Okay, hello everyone. Mm, it's time, but I'll wait for a couple of minutes just in case anyone wants to join for this live session. This is our final live session, so I'll wait for a couple of minutes before we start. Okay. Okay, so I guess we can start. So, firstly, let me write down briefly all the important concepts that were discussed in the week 12 uh, class material, and these will be helpful throughout this session. We will be using these to solve problems. So let's get them straight right away. So okay. Okay, so firstly, molecular energy levels and spectra. So primarily there are three of them. First is electronic energy levels. Okay, and electronic spectra, like hydrogen spectra, for example, or spectra for hydrogen like atoms, where these energy levels are the electronic energy levels, which are also known as Bohr levels, right? Secondly, we have rotational energy levels. Now, these energy levels arise because of rotational degree of freedom of a molecule, right? So, molecule can rotate, and because of rotation, it has a rotational energy. This rotational energy is quantized, and this quantization gives us rotational energy levels and correspondingly rotational energy spectrum. Finally, we have vibrational energy levels. Okay, these occur because molecules vibrate, and these vibrations have certain energy. Again, this energy is also quantized, therefore we get levels and a corresponding spectrum. Okay, so let's move on to this will be more of a focus for today's problems, which is Raman effect. Okay. So what is Raman effect? It is inelastic scattering of light, which is just photons, right? By molecules. Okay. So what is Raman effect? So Raman effect is basically that when a light interacts with matter, okay, and matter is made of molecules, then the molecules can scatter the light inelastically. So this word is important. Okay, inelastic scattering. So whenever we have inelastic scattering, what happens is we lose some energy or we gain some energy. Okay, so the photon, either it can lose some energy upon collision or it can gain some energy. Okay, therefore it will have a different frequency after scattering. Okay, now where is this extra energy going to or coming from? So this extra energy is taken up by molecule or given by the molecule from its rotational energy modes. Okay, we also have another scattering which is known as Rayleigh scattering. So how is it different? It is different because this scattering, this is elastic, right? So this is elastic scattering. Here both the scattered and the incident light have same frequency. Okay. Then we have something known as selection rules. Okay. So firstly, for Rayleigh scattering, the rule is delta J is equals to 0. Now this should make sense because this is elastic scattering. So the rotational energy is not going to change. Therefore, the rotational quantum number J is not going to change. So delta J is 0. Next we have Raman scattering. And here delta J changes by plus minus 2. Right? And thirdly, for vibration, we have vibrational quantum number V. So V changes by plus minus 1. Okay, so these are the selection rules. Okay. So now we have something called Stokes and anti-Stokes lines. So what is a Stokes line? So this occurs when molecule absorbs energy. So when the molecule is absorbing energy from the photon, so the final scattered photon will have lower energy and therefore lower frequency. So scattered light has lower frequency. Or higher wavelength. Than the incident light. Fine. Similarly, we have anti-Stokes line. So these lines occur when molecule loses energy. Okay, so molecule loses energy and scattered light will have higher frequency, right? Basically opposite of what is happening in the case of Stokes lines. Okay, so yeah, these are all the topics which were discussed in this week's classes, and obviously there are some equations as well which I will write down when required as we go on solving some problems. Okay, so I guess we can start solving some problems. Okay, let's start with some conceptual ones. Okay, so let me write question. Question number one. Okay, So, as we discussed few minutes ago, there are primarily three types of energy levels we are concerned about: the electronic, vibrational, and rotational energy levels. And now, when we do spectroscopy, we want to know in which region of the spectrum, we will find the corresponding spectra for these three different energy levels. Okay. We are given three options: infrared, far infrared, microwave, UV, and visible. So we will start off with noting that energy of electronic spectrum or electronic levels is roughly of the order of 10 eV. Energy of vibrational levels is roughly of the order of 0.1 eV. And finally, energy of rotational spectra is of the order of 10 to the power minus 3 eV. Okay. Now we know that in terms of light, energy E is nothing but hc over lambda, right? And if this is written in terms of electron volts, so what we can do is we can write lambda is equals to hc by ev. Okay, and now we know the value of all these universal constants. So basically lambda comes out to be 1240 divided by V. Okay, or your energy which is in electron volts. Okay, so for example, our 10 eV energy, this will correspond to 124, and this is in nanometers. This will correspond to 1240 by lambda. Okay, so this implies that lambda is roughly 124 nanometers. Okay, similarly 0.1 eV will give us lambda is 12400 nanometers. Or roughly 12 micrometers, 12.4 micrometers. If we put 10 to the power minus 3 eV, this will just give us lambda as 1240 micrometers, or basically 1.24 mm. Okay, so we can write these values. So this is roughly 120 nanometers. This is roughly 12 micrometers, and this is of the order of roughly 1 millimeters. So now if we look at our options from here, clearly this 120 nanometers, this corresponds to UV, right, ultraviolet, because the wavelength for violet light is around 340-350 nanometers, and we are increasing the energy, so it is going to UV. So therefore, for electronic energy levels, we have UV and visible spectra. Okay, so which means we can eliminate option B and option D, because first will be C. Okay, then for vibrational energy levels, we have this to be micrometers. Okay, roughly 12 micrometers. So this will corresponds to the infrared spectrum. This is infrared, and finally this is 1 mm, so this is far infrared, right? Far infrared or microwave, which means 2 goes away, so this is the correct option. So you can also eliminate this. Okay. Yeah. So this one goes here, this one goes here, and this one goes here. Yeah, like this. So that's good, which means question 1 is done. So we can move on to the next one. Question 2. Very straightforward problem. Okay. So, as we discussed above, when we were discussing Raman's scattering, so here it is, Raman effect. So what is it? It is inelastic scattering. Okay, it is inelastic scattering of light by molecules. Right? We have clearly mentioned molecules. So let's get back to our problem. Here, Raman effect is a scattering of light with molecules. So option B. And we can also write here inelastic scattering of light or photons with molecules. This is the Raman effect. Very well. Let's solve the next one. Question 3. Okay. let's do this one. So what is the question asking us? It is asking us to identify the wrong statement or statements. Okay, the wrong ones. Okay, so and here we have three statements, and the first two statements are the selection rules. One is for Raman scattering and the second one is for Rayleigh scattering. So we discussed in the introduction of this one about selection rules. So here we have clearly written out the selection rules for Rayleigh scattering delta J 0 and Raman scattering delta J plus minus 2. Let's go back. Let's check. So delta J plus minus 2 for Raman and delta J 0. So statement 1 is correct, statement 2 is correct. So therefore by process of elimination we can say that statement 3 is incorrect. So this is the only correct option. Now let's see why statement 3 is incorrect. So what they are saying is they are talking about Stokes lines, right? And they are saying that the wavelength of Stokes lines is shorter than that of the original line. Okay, so if we have light coming in here of wavelength lambda, it interacts, and then the photon coming out here. So this lambda prime, this is less than lambda. This is what statement 3 is saying. Okay, now we know that we get Stokes line when the molecule absorbs energy. Okay, let's go back to our notes. Here clearly written that molecule absorbs energy, okay, during scattering. So when it is absorbing energy, therefore the scattered light will be of lower frequency, right? Because energy is h nu. Now some part of nu has gone to molecule, therefore the scattered nu will be less, and when frequency is less, the Stokes lines have higher wavelength. Okay, Stokes lines have higher wavelength, and this thing is wrong. This statement says that they have shorter wavelength. So for Stokes line, lambda prime is actually greater than lambda. Okay, therefore option C is the right option. Fine. So that was the third question. Let's move on to fourth one. Okay, so let me have some water before we start solving this. Okay. Hmm. So, okay. So the question is asking about the gap between two consecutive Stokes or anti-Stokes lines in rotational Raman spectra, and it is asking in terms of wave number. Get. Notice that we are already given the energy, rotational energy. Okay. So E rotational is given to us to be HCBJ J plus 1. Right? So for the corresponding wave number, which is generally denoted by mu bar. Mu bar is 1 over lambda, right? And writing in terms of energy, so this is Hc by E. No, E by Hc. Sorry, my bad. E by Hc, because energy is Hc by lambda. Okay, so if we plug the rotation energy in terms of E, what we will get is HCBJJ plus 1 divided by Hc. So these terms will cancel out, and we will get nu bar as BJ J plus 1. Okay. Now we also know that the selection rule is delta J is plus or minus 2. Correct? So we can write delta nu bar as B times, so this will be 2J, and 2J plus 1 minus B times J and J plus 1. Okay, so this becomes 2BJ plus 4BJ squared minus BJ squared minus BJ. No. Okay, I made a mistake. Let's do it again. So So it will be b times j plus 2, j plus 2 plus 1 minus b times j, j plus 1. Yeah. So this will be bj plus 2b times j plus 3 minus bj and j plus 1. We can write this as bj plus 2. Okay, let's take b outside. Then this becomes j squared plus 5j plus 6 minus j squared minus j, right? So this cancels out and this becomes 4j, right? And this becomes 6. So if we take 2 common, 2 gets outside, so this becomes 2b and it becomes 2j plus 3. Right, so finally we have delta nu for Stokes or anti-Stokes. This is nothing but 2b 2j plus 3. So this is the Raman shift, right? So this is in terms of b and j. This is what we get. Okay, so for now the question asks us for 2 consecutive Stokes line or anti-Stokes line. So for 2 consecutive ones, what we need is we need delta nu bar j plus 1 minus delta nu bar at j. So we need this. Let's plug in j plus 1 here. So this will be 2b 2j plus 1 plus 3 minus 2b and this is simply 2j plus 3. So let's simplify. Let's take 2b outside. This becomes 2j plus 2 plus 3 minus 2j minus 3. This will cancel out and this will cancel out, giving us simply 4b. Okay. Therefore, gap between 2 consecutive Stokes. Therefore, gap between 2 consecutive Stokes or anti-Stokes lines in terms of wave number is 4b. Let us check our options. Yeah, option A. Okay, so we started with the rotational energy, then we converted that to, not converted, but then we have written it in terms of wave number. After that we applied selection rule, and from selection rule we get this relation delta nu bar 2b 2j plus 3. Okay, so the selection rule is embedded into it. Therefore we can get the separation between 2 consecutive. So for 2 consecutive it will be j plus 1 and j, or j and j minus 1, doesn't really matter, and this will give us the suppressed. Okay, and this comes out to be 4b units in terms of wave number. Great. So let's solve next one, which is question 5. Okay, so this is our question, and we are using a laser. The wavelength of laser is 546 nanometers. So in case of Stokes line, we know that the molecule has absorbed some energy, therefore the light emitted will have a longer wavelength, and that is indeed the case. So its wavelength has increased by 6 nanometers. For anti-Stokes line, we know opposite will happen. Our wavelength will reduce. So from 546, it will go below. So all the options are less than 546. And now we want to figure out which is the correct one. Okay. So let us define some notations. So let's say this is the wave number, the original wave number, right, of laser. Okay, this is wave number of Stokes line, and this is wave number of anti-Stokes line. Okay, So having defined this, let's write the Raman shift. So this is the Raman shift, right? So the wave number of laser minus the wave number of first Stokes line, this will be equal to wave number of anti-Stokes line minus the original wave number, right? Or the wave number of laser. So from here we can write wave number of anti-Stokes line to be 2 times the original wave number of laser minus the wave number of Stokes line. Now what the question asks is the wavelength, right? Question asks about the wavelength. So let's convert wave number to wavelength. Now we know that wave number is the inverse of wavelength. So nu bar is nothing but 1 by lambda. Right? Therefore, we can write 1 over lambda anti-Stokes is 2 over the original lambda of laser minus 1 over the wavelength of Stokes line. Okay, so this becomes 2 times lambda s minus lambda naught over lambda s lambda naught. Okay, therefore lambda a is nothing but lambda s lambda naught divided by 2 times lambda s minus lambda naught. Okay, now what we know that lambda naught is what 546, yeah, 546 nanometers, and lambda s was 552 nanometers. So let us plug in the values. Lambda a will then be 552 into 546 and 2 times 552. So this is 4011 minus 546. So this is 552 546 and this is 8 and 5 and 5. So this thing, let me put this in the calculator. 552 546. So lambda a comes out to be 540.13 nanometers. So this is the wavelength of first anti-Stokes line. Let's look at our options. So option A is the closest one, which is 540 nanometers. Okay. So this was our fifth question, which basically relied on this one concept of Raman shift. Okay, so this thing. So this is the Raman shift, and the Raman shift remains same for first Stokes line and for one first anti-Stokes line. Okay. So let's solve one more problem based on this Raman shift. That will be question number 6, I guess. Hmm. So this is our sixth one. Okay. We have already solved one very similar problem. Here again we are given the rotational energy, right? And we are asked the answer in terms of wave number. So this is the question similar to question 4, right? And what the problem is asking us is the difference between first Stokes and first anti-Stokes lines. So this is the question. Okay, again we are given energy. Okay, so from this, as in question 4, we can clearly write this thing. Then we have selection rule. This is the selection rule, and from selection rule we get 2b 2j plus 3, right? This is what we get. Let's check. Yeah, here, this one. So we start with same equation, mu bar, put the selection rule in, that delta j is plus minus 2, and then we solve for this delta nu bar. Okay, we just plug in, simplify, and we get this value 2b times 2j plus 3. Okay, so this much we have already figured out. Great. Now what the question is asking us, the difference between first Stokes and first anti-Stokes lines. So that will be in terms of wave number, Stokes, and anti-Stokes. Okay. So what is this? This is the Raman shift, right? This is the Raman shift. Let's say it falls somewhere here. Here. So as we already know that the first Stokes and first anti-Stokes lines. So let's say this is the Stokes one and this is the anti-Stokes one. So this distance, they are same, right? And this one distance we have already calculated to be 2b 2j plus 3. Okay, this is 2b 2j plus 3. So therefore this difference, let me erase this, or maybe I can pull this down. Yeah, here it is fine. So therefore this will be 2 times delta nu bar, or 4b 2j plus 3. Okay. So this is what we have. Now for first Stokes or anti-Stokes line, for first Stokes or anti-Stokes line, J is 0. Therefore this entire thing, let me paste it here. So then this becomes 4b 2 times 0 plus 3, or simply 4b into 3, which is nothing but 12b. So let me again paste it here. This thing is nothing but 12b. Okay, let's see. Yeah, here it is. So that is our answer. So this was the 6th question, and it was very similar to the 4th question. Only thing that we used extra is the concept of this Raman shift. We know once we have calculated this difference in wave number for one, so this difference is just between the Stokes and anti-Stokes is twice of that, so it then becomes 2 times delta nu bar. Okay, and this is 4b 2j plus 3. Other thing is that we plug in j is equals to 0 for the first Stokes or anti-Stokes line. Doing this gives us the difference in terms of wave number to be 12b units. maybe we should put units here. Okay, so this was question number 6. Let's move on to 7th problem for the day. Okay, again one very similar type of problem. Only difference is that we are required to calculate the moment of inertia. Okay, so we should first, before starting this one, we should first note that the rotational quantum or the rotational constant B is related to moment of inertia. By the relation B is equals to h over 8 pi squared IC. Okay, let's call this as the first equation. So then this question boils down to finding out B. So we will calculate B from Raman spectroscopy and then use this B to find out moment of energy. Okay, so let us begin. Now what is given? That we are given that gap between two consecutive Stokes lines is this much. Now this sounds familiar. So in question number 4 we said that gap between two consecutive Stokes or anti-Stokes line is equals to 4b units, right? So we do not need to solve this again. we can simply borrow this concept, this answer, that the separation between two consecutive Stokes line is 4b. And the good thing is, uh, it is already given in terms of wave number. You can see it is per meter, correct? So we can directly write that 4b is 4160 per meter. Okay, so let's write, we know uh, we know from question number 4, the gap between two consecutive Stokes lines in terms of wave number is 4b units, and here it is given to us to be 4160 per meter. This implies 4b is 4160. Okay, so this is what we have, right? So this would give us b to be 1040, I guess. Yeah. So this is b. Let's call this equation 2. So we have done with calculating b. Now substituting in 1, substituting in 1, we get 1040. This is h over 8 pi squared IC. Sorry. Or this implies I as h over 8 pi squared times c into 1040. So let's plug in all the values. This is 6.626, 6.626 into 10 to the minus 34. This is it. This is pi squared. This is 3 10 to the 8. And this is 1040. This becomes 6.626 divided by 8 pi square, or let's write 24, into 1040 into 10 to the power minus 42. So let's plug it in a calculator. So this comes out to be 2.69 into 10 to the power minus 5. And we already have minus 42 here, so that will make it minus 47. And this is kg meter squared. So let's put it in a box. Great. So this is 2.69. Yeah, closest to option B. Okay. So what this means? This means that we can use Raman spectroscopy to find moment of inertia of the molecule. And you can see that this number is very very small, but still we are getting a very good approximation for moment of inertia of a linear diatomic molecule. Okay, just by doing spectroscopy. Okay, so yeah, that's good. Let's do next question, question number 8. Okay, question number 8. And what is it asking? This is asking about vibrational Raman transitions. V is vibrational quantum number, and here we are given some transitions. So the vibrational quantum number, it is changing between 1 and 2, 1 and 3, 2 and 3, or 3 and 4. Now the question is asking that which one of these is actually wrong. Okay, so if we go all the way back, uh, first notice this is about vibrational spectroscopy, right? Vibrational. So all the questions which we were doing till now were mostly rotational spectroscopy, rotational transitions, and there the quantum number is denoted by J. Here it is V, and we are talking about vibration. So now let's go back here. Here are our selection rules. And if we look at the selection rule for vibration, it says that delta V is plus minus 1. Okay, now let's go back. Yes, here we are. So selection rule, let me write here. Selection rule gives us delta V plus minus 1. Okay, so what is the delta V here? Here delta V is plus minus 1. Here delta V is plus minus 2. Delta V is plus minus 1. Again delta V is plus minus 1. Okay, so we can clearly see that this is the wrong one, and we are asked that which of the above is wrong. So correct answer is V is equals to 1, 2, 3. So this transition violates the selection rule. Okay. So pretty simple and straightforward problem. Let me take a break for a couple of minutes and have some water. Okay. Hmm. Sorry for the break. Uh, how many have we done? 8, right? Yeah. Let's do a couple more, and I think then we can call it a day. Let me read question number 9. Okay, so we are given a Raman line and we are given one exciting line. Okay, and notice that the units are in angstroms, and what we are asked is to calculate the Raman shift. And here note that the units are in per centimeter. Okay, per centimeter. So let us first deal with exciting now. Exciting line. Okay, so wavelength lambda, it is given to us as 2500 angstroms. So wave number, okay, let's write this in terms of centimeters. So this will be 2500 10 to the minus 8 centimeters. Wave number, nu bar is 1 by lambda, or simply 10 to the power 8 divided by 2500 per centimeter. Okay, so let us find out this value, or okay, let's leave it for now. And the other one is Raman line. So here wavelength lambda is 2575 angstroms This is 2575 10 to the minus 8 centimeters. So the wave number nu bar, which is 1 by lambda, it will be 10 to the power 8 over 2575 centimeter inverse. Okay, so let's call it, because this is exciting E and this is Raman R. Okay, Raman shift delta nu bar, it will be given by mu bar E minus mu bar R. Okay, now we have all the things. So this we know is 10 to the power 8 divided by 2500, and this is 10 to the power 8 divided by 2575, and this answer will be in per centimeter. Let's take 10 to the 8 outside, and inside we will have 2575 minus 2575 minus 2570 divided by 2500 into 2575 per centimeter. So this is nothing but, this is 2500. Okay, so this is nothing but 25 and 2500 into 2575 per centimeter. So let's find out this value. 25 divided by 2575. Okay, so 10 to the power 8. And this comes out to be this much. So we can write it as 1165 per centimeter. Therefore, the Raman shift is 1165 per centimeter, which is option A. Okay, so yeah, it was a fairly simple problem. So we were given the wavelengths of Raman line and the exciting line. We just need to convert these to wave numbers, because the Raman shift is given in terms of wave numbers. You can also see that from the options that they are asking in terms of per centimeter, which is the units of wave number. Okay, so then we converted lambda to wave number for both the lines and took their difference, and that difference is known as Raman shift. Okay, here. So that is our So, so let's yeah. Let's write down the next question, which will be question number 10. Okay, so this will be the last problem for today, and it is about again Raman spectroscopy. So we are given wavelength of the exciting line. Okay, here you can see that the wavelength of the exciting line is given, and it is used on a material. So we get Raman line of 5000 angstroms. Okay, good. Then what the question asks is the find the position of Stokes and anti-Stokes lines in angstroms for the same material when the exciting line is 4000 angstroms. So earlier it was 4900 angstroms. Now it is 4000 angstroms. Okay? So the wavelength of exciting line has now changed. And the question already has a hint on how to solve this one. So they say that the Raman shift is the characteristic of a material irrespective of the wavelength of the exciting line. So to solve this problem, this is the important line that Raman shift does not change with exciting so Raman shift does not change with exciting wavelength. So we are given two exciting wavelengths. Okay, so lambda E1 is given to be 4900 angstroms and lambda E2 is given to be 4000 angstroms. Okay, so no matter which wavelength we are using, Raman shift will not change. So let's find out the Raman shift for the first case, and then we'll use the same Raman shift to find the Stokes and anti-Stokes line in the second case. That is the strategy. Okay. So this comes out to be 20408 per centimeter. Okay. So this is given us as 5000 angstroms. So this will become this, and this will come to 0.04 here. Okay. So now we have both the wave numbers, and we can calculate the Raman shift. Thus the Raman shift is 20408 minus 2000, and this is simply 408 per centimeter. Okay, so let's calculate the wave number. Wave number corresponding to second exciting line, that will be nu bar E2 10 to the power 8 over 4000, and that simply comes out to be 25,000 per centimeter. Okay, now since Raman shift remains the same, Raman shift remains the same, wave number of Stokes and anti-Stokes lines will be so nu E2. Okay, let's write this as delta nu bar E2. Okay, because we are writing Stokes first, so this will be minus and anti-Stokes will be plus, and delta mu bar, which is the Raman shift. So this becomes 25000 minus plus 408 per centimeter. So on subtracting, we get 24592, and on adding, we get 25408 per centimeter. So this is Stokes and anti-Stokes. To convert to wavelength, so lambda of the Stokes line, this will be 24592. Okay, and this will be in centimeters, so we'll multiply this by 10 to the 8, and this will then be angstroms. Similarly, that of anti-Stokes will be 10 to the power 8 divided by 25408, and again this will be angstroms. So lambda S comes out to be 4066.3 angstroms, and lambda anti-Stokes comes out to be 3935.7 angstroms. Here, so 4066 and 3935. So option C. So yeah, this was the last problem for today. And for this course, it basically involved calculating the Stokes and anti-Stokes line when we use a different exciting line. The key concept is that the Raman shift remains same irrespective of the wavelength of the exciting line. Okay, and it is a characteristic of a material. So even in the laboratories today, Raman spectroscopy is one of the best techniques which people use to characterize a material, because this Raman shift is like a fingerprint of a material, and it is independent of the wavelength of exciting line. So yeah, this tells you about different molecules present in your system, because all of them will produce a characteristic Raman shift. So yeah, I guess that's it for today. That's it for the tutorials of this course. I hope I could help you understand some physics by solving some problems. Although the attendance in the live sessions was less, still I hope that you guys are watching it on YouTube and it is helpful in solving your assignments and understanding the concepts taught in the class in a better way. So again, if you have any doubts, you can write in the forums, or you can email me, or you can leave comments on the below the YouTube videos. So thanks for watching. So I'll end the session now. Thank you.